Thanks a lot, Ken, for organizing this, and Mark, this is a great event, and it's just wonderful to see so many friends from economics and people I've heard about and read and admired from climatology and other areas. And it's good to see you. So I'm an economist, but for those of you who are not in economics, you may be interested to know that you can't get a PhD in economics without essentially get a PhD in statistics as well. So we torture our graduate students by, well, I shouldn't say that, by putting them through econometrics, and particularly at Yale, which is a place where we like to think we're really good in econometrics. So we go through that, and anybody who's been through the graduate program here knows about it. So I actually want to talk about statistics more than anything else, more than economics. But it's statistics that I think would be relevant for our economic models. I hope you think will be relevant, and is actually applied to some climate data. So let me motivate this. So there was a recent. So I want to motivate this with a lesson from finance. There was, I'm sure you know, there's this recent Nobel Prize, including to a Yale economist for finance. It was actually in economics, but it was really finance. And I think as I looked at that, the lesson from the three people, were that what they were doing was they were taking a combination of powerful theory, very, very rich data. The data in finance are richer than any place else in economics, and very sophisticated use of statistics, and getting really rich findings, really powerful findings. And the one that I'm particularly live in awe of is the history of the discovery of the random walk hypothesis. All of you probably know that stocks are supposed to move like a random walk. The history of this is really interesting because it goes back to some physics and then picked up by economists. I point particularly to Samuelson, and then Fama and Schiller, who took roughly the same data and got pretty much opposite conclusions, but that's okay. Fama was looking at the very, very short run, and Schiller was looking at the very, very long run. And here's a paper that I'm sure Marty remembers this and Jeff Heel, but I remember reading this paper that Paul Samuelson wrote, and I remember when I read it, I just couldn't believe it. The proof that perfectly anticipated prices fluctuate randomly. And that is such a counterintuitive notion that somehow when you anticipate things perfectly, they move randomly. I just remember when I first read that, I just shook my head. This is just like, it was, I suppose, like quantum physics, the discovery of relativity. It's just like, it shook the whole way I thought about the world. And I won't go into this, but it's a beautiful paper. It has some historical roots as well. But then this was basically what Fama and others used, this theorem, and then put it to data and some pretty interesting statistics and then we have where we are today, which is the idea of the random walk hypothesis and all its implications for finance, good and bad for finance and crashes and things like that. So now I wonder, I'm a little, this is a little provocative, but I just raising a question whether might be also in some of the key parameters that we're using that we need for our models, and some we've talked about today, some we haven't, whether it might be a fruitful approach there to use. I am impressed as I look at climatology and paleoclimatology, beautifully rich data. It's just amazing, the data. The ice core data, I think, is just one of the most beautiful sets of data I've ever seen in my life. I just am in awe of those data. And the combination of that and some statistics and theory might actually give us some interesting results. And I don't want to be too negative, but it looks to me as if there are some diminishing returns in building more and more models. Now, maybe we just haven't hit that threshold. You get down to more resolution and faster computers and the super hyper computers, and maybe we're going to cross some threshold where it's just, when we get down to 1 kilometer resolution, that's where the problem is. And when we get down there, whew, everything will suddenly become clear. Maybe so, I don't know. But they're pretty clearly, just as you look at what's happened, we haven't resolved things like the temperature sensitivity. Okay, so I'll just say I have two puzzles. I'm only going to talk about one in detail, but I do think this diagram, which Ken showed earlier, and many of you from the climate sciences know this from the 5th assessment report. This, I'm quite sure it's sort of the distribution of PDFs, and then the distribution of PDFs, and then this strange combination at the bottom that I haven't yet to understand how that was arrived at. But one question is whether we could better use these results in the spirit of meta-analysis, which is used not used at all in economics. I don't know if it's used in climate and earth sciences, but in the spirit of meta-analysis, whether we can combine these data to improve the precision. Now, I know Jeff Heal doesn't like this idea because he wants to. He doesn't want to see these, and I sympathize with that point of view. But from the point of view of this classical statistics, whether we could improve these combinations. It's a very complicated problem because these are not independent. So these are not independent clinical trials where you get 1,000 patients from here and 1,000 patients from there. A lot of them are quite dependent. They're using the same data sets. So you have to be very careful. But I do think it would be very fruitful for some statistician who's interested in meta-analyses to see how you could take these, combine them, take into account the dependencies among the different data sets, and get some kinds of combination. Maybe that was how it was done, but Ken and I are trying to track down how it was done, and we've been worrying about this. Maybe Ken, since I last talked to you, knows how the combinations have been done. But anyway, I would be very grateful if any of you, I would be on my knees, like Hank Paulson with Nancy Pelosi. I'd get on my knees if you just could tell me how they were done.
In 20 minutes.
Okay. But that's not what I want to talk about. Okay. What I want to spend my 10 minutes or so on is this untangling the paleoclimatic data. I think all of us must have looked at this something like this, which is the CO2 and temperature proxy data over the last 400,000 years. Yes.
Let's get this a little bit better.
I'm sorry. How's that better? All right, I'm sorry. So you missed half of it, but it's okay. Well, it wasn't worth hearing. So this is the second half. So as I said, I'm sure all of us have looked at that and said, gee, that's kind of something's going on here, and these are and you just can't, and of course some people say, oh, CO2 is obvious that CO2 is causing temperature change. Just look at this diagram. And other people resist that. But I look at that and I said, there's something going on here. Can't we untangle that? And of course, this was the first thing that comes to mind. Well, which is the chicken and which is the egg here? That's it. This is a good question. So I assume that's the reason we haven't figured it out, is because it's a chicken and egg problem. So what I'd like to suggest, so this is something that would be familiar to many of the economists, but maybe not, I don't know, to the earth scientists. But what I'd like to suggest is there is a technique that might be useful in a lot of applications of statistics to the geosciences, where you have multiple data that are going on at the same time with chickens and eggs, and you don't know the directionality, which is called simultaneous equation estimation or instrumental variable estimation. Those are a little different, but for this purpose, they're about the same. And I assume that not all of you know about it, or I will just end if you all know about it, but it's worth talking about. So we know that the CO2 and the T are highly correlated from that picture, but it's not obvious the extent and the direction of the feedbacks. And now I'm sorry. Now, most geoscientists I've talked to, and Mark and I have talked about this, have a pretty clear view about what's going on. But the question is whether you can use statistical analysis to either confirm or not confirm that. And so this is what I want to do is suggest you can use an instrumental variable approach to find out which is chicken and which is egg. There's a little bit of history there. There's a paper by Kaufman, Kauppi, and Stock, which is not quite on the subject. And then there's a really interesting paper by Derek Lemoine, which is almost identically on the same subject, although he did it a little differently. And so in a way, what I'm doing is showing what Lemoine showed in his paper, but in a slightly different, he used a slightly different framework. Okay, so let me go through the statistics quickly. So what I want to assume is you have a system like this, where you have temperature as a function of CO2. CO2 is a function of temperature. There are some exogenous forcing variables, M and Z. They're random errors, but now you put lags in here. It's not going to change it, and I'll put lags when I do the empirical. But for the purposes of this, you want to say that both affect the other. We talk a lot about CO2 concentrations affecting temperature, but we also know that it goes the other way around. So the key insight is, well, the key question is: are there other variables that affect temperature and concentration, but don't affect the other? So are there variables which are exogenous that affect these but that affect the chicken but don't affect the egg? And the one that I'm going to particularly focus on is well, let me just say, this yields, just to go through a couple of technical points, this will yield what's known as a reduced form, which is a technical term from statistics, where what I've done is I've taken this and I've solved for the left-hand side variables as a function of the exogenous variables and the disturbances, but we've removed the simultaneity from this, so all of these are either exogenous variables or they're random independent errors. And then you can actually, so if you solve this, you're going to come up with, if you do run a ordinary least squares estimate, you're going to get an estimate of this, which is actually not equal to alpha. And it's actually, you can show with a little work, it's actually going to be greater than alpha, but it's going to be a function of the variance of the errors, the variance of, I've taken out the z because it's not important for this, the variance of the m and the variance of the u's. So unless you're very, very lucky and some of the variances are 0, you're going to get a bias coefficient. And generally, you'll get a coefficient that's biased upwards. Now, what I'm going to do later is I'm going to use orbital variables, M for Milankovitch, orbital variables as instruments here. And the key assumption is that the orbital variables affect the climate, but they don't affect CO2 concentrations except through their effect through climate. Right? So now maybe it's wrong. Maybe when precession occurs, a little rock weathering occurs or something like that, but I think probably not. I think it probably is the case but it's critical to this that it affects CO2 concentrations only through its effect on climate. Now, the z variable would be the opposite. Z variable affects the carbon concentrations without affecting the climate, and I don't know of a z variable, unfortunately. It's really too bad, but if we had a z variable, we would really be very, very happy pups. Okay. So the key point, though, is if you have a simultaneous system, the reason you can't untangle that chicken egg because you have a simultaneous equation bias, which is this complicated tangle of things, and it just takes a little work to prove that's greater than alpha. That's assuming that the beta and the theta there are positive, or that the beta is positive. So now, so there are couple of points here. First, these equations are not identified. That's a technical term. That means you can't figure out what the parameters are without further assumptions. So one approach is to use these orbital variables. I've done a lot of instrumental variable work over my long life, and I've never seen actually such a beautiful set of instrumental variables. Maybe time is exogenous, but almost every other instrumental variable we use in economics, you can think of some indirect feedback effect. But it actually looks, I'm sure I'm going to be told I'm wrong, but it sure looks to me as if orbital variables are ones that affect the climate but don't directly affect CO2. And if that's the case, then you're really, really a happy statistician. Now, as I say, in my conversations with people, have not found any instruments to identify CO2. So if you have some that you know about, let me know. But if you could do that, you could get a lot further. We can only solve half the problem with this set of identification assumptions. So what I'm going to do is I'm going to go and identify the parameter, the feedback parameter, so the parameter from temperature to CO2. That we can very, very closely identify, but we can't identify the temperature sensitivity coefficient from CO2 to T because we don't have an instrument there. It might be possible to use higher order moments to do that, but and that's very popular in econometrics, but I don't like it very much because it's less, I think, much less persuasive, and it requires all kinds of assumptions. But I think it's possible you could do that too, but I haven't done that today. Okay. So let me just show you. So what I did was, the equation was so the simple equation of log of CO2 concentrations on temperature and log of CO2 concentrations with these random variables, and then the Milankovitch variables in the temperature equation. And then if you run an ordinary least squares estimate of that, you get a parameter of 0.0224, which is actually pretty close to what you get in some of the general circulation models, I'm told. And if you run it with an IV estimate, you get almost identical estimate, which is actually quite surprising. And just so that you know, here I don't really know what, I mean, I would use advice here, but presumably the climatologist would know what the relevant lags are. Clearly it's not just current orbital variables, but current and lag orbital variables. I just used current lag 1 kiloyears and 5,000 years. Once you use those, it doesn't seem to make much difference to the estimates. You could put in 10,000 or 3,000, it's about basically the same results. The data set is what I call the standard data set, the Vostok ice core, proxy, and CO2, and the Milankovitch is standard Milankovitch data. There are a lot of, I'll get in if we wanted there are a lot of technical issues, statistical issues that mean it's a little more complicated than the story I'm telling for lots of reasons. Interpolation, autoregressive errors, moving average errors, interpolated data, all kinds of issues in rise of that. But I think those are technical issues. Really, I want to show is that there's a technique you can use to disentangle the chicken and egg. So what this does suggest is that the fact that these coefficients are close is that most of the variation is coming from the orbitally driven temperature. And then it actually gives you a pretty clean estimate of what the feedback is. And it says that if you have a 3 degree rise, that if your concentrations are 500 ppm, that you'd get an additional feedback effect of about 33 ppm, which I think is in the ballpark of some of the models I've looked at. So I think the main takeaway here is there is a technique where you can break this chicken and egg problem. It requires a lot of very careful data work, which I haven't done, and a lot of careful examination of what kind of biases there are, particularly in the estimates, because of the air properties of the residuals. But it can be done. And just so that this is a picture from this data set, this shows you the actual CO2 concentrations in blue, and then the other two lines are the estimates of the amount that are driven by temperature in the OLS, ordinary least squares, which is in green, and the instrumental variable, which is in red, and you can see they're very close. Not perfect, they get the major cycle, but the main thing is that it looks as if that you can use this, and there's not a huge bias in the OLS in that parameter anyway. Now, so you could actually go back and estimate the temperature equation. I did this, and this is the alpha parameter. You multiply that by about 0.62 to get the temperature sensitivity. That's the temperature sensitivity in Antarctica. But this is an upper bound from the theorem on the bias. This is an upper bound. And so I actually think that I presented this once when Marty was there, and he didn't like it. He told me how all the mistakes there were, and there still are there, although I did a little more to take into account his comments. But in terms of, I thought, when I first did this, can't we chop off that upper tail in Marty's fat tail distribution? And I would claim modestly, I mean that modestly, that actually this is a way of chopping off the upper tail, because we know that it's pretty tightly determined. You can see from the t statistic there, although it's probably biased downward or biased upward. You can see that it's a pretty well determined coefficient, and we know that this is upward bias of the true alpha. And just so that's, if we multiply that by the log of 2, that gives you 8.7 degrees sensitivity at Vostok upper limit, and I used a 3 to 5 ratio to get global, which gets you down to about 5 for an upper limit. Now, I think you can do better than this if you're looking at the error variances, but I haven't quite figured out how, and so I'll just leave it at that. Okay, so I'm going to wrap up. I think what I've suggested is that the combination of good theory, good data, and statistics can actually bring information to this question that's of pretty great interest, at least to economists, and I think actually more broadly. But the instrumental variable can only, at this point, reliably do the CO2 temperature part of, because we only have that one set of instruments, and we can't yet do we only do the TCO2 and can't do the CO2T, which is actually what we're probably more interested in. And to do the CO2T equation, we would need an instrument, as I said, something that affects CO2 concentrations without affecting temperature. So if you could think of something, I don't know what it would be. Some fantastic thing. Maybe there's some solar thing that leads to greater weathering. I have no idea, but I'm sure Mark does. But something that leads to, I mean, if volcanoes burped up vast quantities of CO2 and were exogenous, that would be the kind of thing you might think. But you need something that's independent of the climate, that's burping up CO2, that you can measure and you can identify. And if you can find that, then you can do the other equation. And I'd be very interested in your ideas. So that's it. Thanks.